Hi class, I just wanted to finish up essentially four force diagrams, but also talk about the last force diagram that we did on class on Wednesday, the box being pushed. And right, I was telling you at the end of class that we couldn't actually make a qualifying distinction between how big the frictional force is relative to the normal force. And I kept saying that it really depends on what's happening with the situation. So for instance, if this box is not moving, then you could make a statement about the relative strengths. If it's not moving, then the person pushing the box is trying to overcome the frictional force. And if it's not moving, then both those forces would be equal, because not moving means no acceleration. Okay, and then you have two additional cases. The person may have overcome the max static friction, and so it's moving with a constant velocity. In which case, actually, the force diagram will look the same. Both the forces will be equal, because if they were unequal, then he would be accelerating. And then finally, right, if he does have the box moving and it's speeding up, which is really the only option that we have. Well, maybe not the only option, so maybe we have two. If it's speeding up, then necessarily his push force is going to be larger than the frictional force. That will be the only way that you will have leftover, a leftover force that would provide an acceleration. He could have it's possible that the box could already be moving and he lets up on the box and the box is slowing down while he's still in contact with it, in which case that would be a reverse situation where his push force is less, and we would have an acceleration in the negative direction and the box would be slowing down. That one's a little more complicated, though. We probably wouldn't just go in the middle of the motion and talk about it. But so, right, it really depends on what's happening with the box itself in order for you to actually explicitly quantify relative lengths of the forces in the horizontal direction. Okay, continuing on, we have a cork floating in water. So our object of interest is clearly the cork. If we make a dot to represent the cork, there is the cork. The cork is in contact with the water. Since it's water, we typically like to refer to that as a buoyant force. F, buoyant. And that's from the water on the cork. And then the earth is down here, and so we have some F grav from the earth on the cork. And in this case, since it's just floating there, more than likely it's stationary. The cork in the water can become more complicated, as you know, right? If you were to push down the cork would want to come back up, and the water will act kind of like a restoring force and like a spring. And so this problem can get a little bit more complicated if you purposely apply an external force to that cork. Okay, next one, we have an airplane. And it's on cruise control and in straight level flight. So planes, thanks to their engines, have their own propulsion forward, which we'll call thrust. The thrust comes from the fuel and it's acting on the plane. If we have it on cruise control, that means that there must be something that balances this force going to the right. So a restrictive force, or a force that restricts motion while in the air, would be drag. That would be from the air on the plane. And like I said, those two ought to be equal if we're going with a constant speed, which is what cruise control means. And then straight and level flight, we know that the plane has mass, so there must be some F grav from the earth on the plane. And if this was the only force, then our plane should fall out of the sky. And so there is essentially a contact force between the plane's body and wings and the air. And this one actually does get a special name, and it's not one of our listed ones, but it's generally referred to as lift, and it's from the air on the plane. And if it's straight and level flight, then by necessity, the force going up needs to be equal to the force going down, and we'd have this balanced force diagram. Okay, two more. We have a ball hanging from the ceiling by a string that's pulled back and release. Identify that force is acting on it just after release. So it's like we're just looking at the ball here. I'll make the ball as a dot. There is clearly one thing attached to the ball, and that is a rope. So we have some F tension from the rope on the ball. And then, somewhere down here is the earth. And so there should be some F grav from the earth on the cork. This one is worth kind of breaking up a little bit. If we're looking at these forces, you could easily break up the F tension force into a vertical component, FTX, a vertical component, FTY, and a horizontal component, FTX. And right when we add those two together, we get the F tension force. And then the only thing that we can really state if we were trying to quantify things is that this vertical force here would end up needing to balance with that gravitational force going down. And then the biggest thing to kind of take note of is that you're left over with this force in the horizontal direction, which provides you reasons for why the ball goes to the right, because there's some unbalanced piece of the force. So there's a piece of it in the horizontal direction that accounts for its motion in the horizontal. Okay. And then last one, hopefully I don't run out of time. We've got two blocks tethered together with a rope run over the pulley. The surfaces are frictionless and the blocks are steady. I think I'm just going to do one of these. So let's just do block A. I'm going to put in my incline off to the side here, and I'm going to put in my block A. So I have two things touching the block. I have a tension force, which is going along the direction of the incline, so tension from the rope on A. And then it's touching the incline itself, but there's no friction. So it's only the contact force, the normal force. So I need to put in an F normal from the incline on A. And then presumably the earth is down here. And so there is a force from the earth on the block of F grav. Okay, again here though, we can break things into their components. Typically we like to make along the incline an x-axis, and then we put in a y-axis to correspond. The F grav then can be broken into two components. It can be broken into a y component and an x component. And then from there we can make some congruency statements. Since the block is not leaving the incline, the normal force needs to balance with the vertical component of the grav force. And if the blocks are stationary, then the F tension force needs to balance with the F grav force in only the x direction. So that would be our force diagram.